Picture a universe where darkness ruled for millions of years. No stars, no galaxies, just an endless void stretching across space and time. This wasn't just any darkness, it was the cosmic dark ages, the universe's most mysterious chapter tucked between the fiery birth of the cosmos and the spark of the first starlight. What happened during this silent era? Why does it still baffle the brightest minds in science today? We're about to dive into 25 cosmic enigmas that will rewrite everything you thought you knew about the universe. From ghostly dark matter shaping the cosmos in secret to entire galaxies vanishing without a trace, each mystery pulls us deeper into the greatest unsolved story of all, how our universe woke up from its ancient slumber. Stick around, because by the end of this journey, you'll see the night sky not just as points of light, but as a puzzle with pieces we're only beginning to fit together. The answers and the even bigger questions are waiting. Now, let's turn our attention to the universe's very first light, or rather, the puzzling absence of it. Imagine the cosmos as a newborn taking its first breath. The first stars, known as population 3 stars, should have been the brightest beacons in that primordial darkness. But here's the twist: astronomers have scoured the skies and found none. These stars are ghostly figures in our cosmic history, leaving behind only questions. What makes population 3 stars so special? Unlike the stars we see today, these giants were pure, made only of hydrogen and helium, the raw elements cooked up in the Big Bang. Without heavier metals to cool their cores, they burned furiously, living fast and dying young. Some theories suggest they were hundreds of times more massive than our Sun, shining with a brilliance that could outshine entire galaxies. Yet, despite their grandeur, they vanished without a trace. So where did they go? One possibility is they didn't just fade, they self-destructed in colossal explosions. These wouldn't be your average supernova. We're talking about hypernova, blasts so powerful they tore the stars apart, leaving nothing behind. Another idea is even more extreme. These stars might have collapsed directly into black holes, swallowing themselves whole before they could leave any visible remnants. It's like searching for a candle that burned out and left no smoke. The hunt isn't hopeless, though. Telescopes like the James Webb Space Telescope are peering back in time, scanning for infrared clues, faint glows that might be the last echoes of these ancient giants. If we find them, it would be like uncovering the footprints of the universe's very first steps. But if they remain hidden, it forces us to rethink everything we know about star formation. Were these stars too fragile to survive, or is our understanding of the early universe missing a critical piece? The mystery of the missing first stars isn't just about their disappearance, it's about how the cosmos took its first leap out of darkness. Without them, the universe might never have sparked the cascade of light and life that followed. Their absence is a silent reminder that even in the vastness of space, some secrets are still waiting to be uncovered. But here's something even stranger than missing stars: an invisible architect shaping the cosmos behind the scenes. Picture the universe as a grand tapestry, and dark matter as the hidden threads holding it all together. Unlike stars or galaxies, dark matter doesn't shine, reflect, or emit any light at all. Yet, its gravitational pull is the unseen hand that molded the universe into the web-like structure we see today. How do we know it's there if we can't see it? Think of it like wind. You don't see the air moving, but you feel its force and sea leaves rustling. Similarly, dark matter's gravity bends light around galaxies in a phenomenon called gravitational lensing, warping the view of distant objects like a cosmic funhouse mirror. Computer simulations show that without dark matter's scaffolding, galaxies wouldn't have clumped together the way they did. The universe would look entirely different: no spirals, no clusters, just a thin, scattered soup of matter. So what exactly is dark matter made of? That's where things get fascinating. scientists have proposed wild possibilities, from undiscovered particles called actions, ghostly bits of matter that barely interact with anything, to WIMP or weakly interacting massive particles. Imagine trying to catch smoke with your bare hands. That's the challenge physicists face. Experiments like the Action Dark Matter experiment use ultra-sensitive detectors chilled to near absolute zero, hoping to catch a whisper of these elusive particles. Meanwhile, deep underground, detectors shielded from cosmic rays wait for the rare moment a WIMP might bump into an atom. The cosmic web of dark matter isn't just theoretical. Telescopes mapping the distribution of galaxies reveal a vast, lace-like structure with dense knots where galaxies cluster and empty voids stretching between them. This cosmic blueprint matches simulations where dark matter's gravity pulls matter into filaments and nodes, like rivers feeding into lakes. But here's the twist: dark matter might not be the only player. Some theories suggest gravity itself behaves differently on cosmic scales, or that our understanding of physics is incomplete. Could dark matter be an illusion, a sign we're missing a deeper law of nature? Either way, unlocking its secrets would rewrite the story of how our universe evolved. For now, it remains the most compelling mystery in cosmology, an invisible force we can't see, but one that shaped everything we can. Now, let's pivot to a mystery that haunts both scientists and dreamers alike: the eerie silence of the cosmos. Imagine standing in a crowded room where everyone has suddenly stopped talking. That's the unsettling vibe of the Fermi Paradox. With hundreds of billions of galaxies, each teeming with stars and planets, why haven't we detected a single whisper of alien civilizations from the cosmic dark ages? One leading theory suggests that life, even if it sparks easily, might be astronomically rare to evolve into intelligence. Picture Earth's own history. It took nearly 4 billion years for humans to emerge after life first appeared. Now factor in cosmic hurdles, deadly radiation, asteroid impacts, or even a planet's own geology turning hostile. Perhaps most civilizations flame out before they can broadcast signals into the void. Then there's the time problem. The universe is unimaginably old, around 13.8 billion years, but the window for detecting techno-signatures might be vanishingly small. Imagine an alien civilization that flourished a billion years ago. Their radio signals, if they ever sent any, would have dissipated into noise by now. Or consider this: what if advanced societies don't use radio at all? Humanity itself is already shifting from radio waves to fiber optics and lasers. Maybe we're listening for the wrong things, like expecting a smoke signal in the age of smartphones. Some scientists propose darker answers. Could intelligent life inevitably self-destruct? Nuclear war, climate collapse, or rogue artificial intelligence might be cosmic filters that silence civilizations before they can colonize the stars. Or perhaps we're just too isolated. The Milky Way spans 100,000 light-years even at light speed. A hello from a distant civilization could take millennia to reach us. But here's the twist: what if we're not silent? The cosmic dark ages were a time before stars fully lit up the universe. Any signals from that era would be drowned out by the afterglow of the Big Bang, or stretched into undetectable wavelengths by the universe's expansion. It's like trying to hear a whisper across a roaring waterfall. The paradox forces us to confront our place in the cosmos. Are we alone? Are we early? Or is the universe hiding civilizations in ways we can't yet imagine? Until we crack this cosmic radio silence, the question remains one of the most profound mysteries of all. Now, let's journey into one of the most dramatic shifts in cosmic history, the moment the universe woke up from its dark slumber. Picture a foggy morning slowly burning away under the sun. That's what happened during the epoch of reionization, when the cosmos transformed from a thick, opaque haze into the sparkling, transparent expanse we see today. But how did this cosmic dawn unfold, and why did it happen in uneven patches across the universe? At first, the universe was a sea of neutral hydrogen gas, so dense that light couldn't travel far without getting swallowed. Then, around a few 100 million years after the Big Bang, something incredible began. The first stars and galaxies flickered to life, and their intense ultraviolet radiation started ionizing the surrounding hydrogen, stripping electrons from atoms and turning the fog into a clear plasma. Think of it like a giant cosmic light switch being flipped one region at a time. Quasars played a starring role in this drama. These supermassive black holes, feasting on gas at the hearts of young galaxies, blasted out torrents of radiation, acting like lighthouses piercing the darkness. Their beams carved out vast bubbles of ionized gas, creating a patchwork of clear and murky regions. Maps of this era, pieced together from distant quasars and faint hydrogen signals, reveal a universe reionizing in fits and starts, some areas blazing bright early on while others lagged behind. But why the unevenness? One clue lies in the clumpy nature of the early universe. Dense regions packed with galaxies and quasars reionized faster while sparse voids remained shrouded longer. It's like how a campfire burns through dry twigs quickly but struggles with damp logs. Another twist comes from the very first stars, monstrously huge and short-lived. They may have kick-started reionization in some areas before vanishing in supernova, leaving others in darkness until later generations of smaller stars took over. The puzzle deepens when we compare theory to observations. Simulations predict a slower, more uniform process, but the real universe seems to have reionized faster and messier than expected. Could there have been unknown sources of radiation, like exotic dark matter particles heating the gas? Or perhaps early galaxies were far more efficient at spewing ultraviolet light than we thought? This epoch wasn't just a cosmic cleanup, it set the stage for everything that followed. Without it, light would still be trapped, and the universe as we know it wouldn't exist. Yet despite its importance, reionization remains shrouded in questions. Why did some corners of the cosmos wake up first? What forces dictated the pace? Each answer we uncover rewrites our understanding of how the universe grew up and how we came to see it at all. Just when we thought the early universe couldn't get any more extreme, enter the runaway supermassive black holes, cosmic giants that defied all expectations. How did these monstrous voids, weighing billions of times our sun's mass, emerge so quickly after the Big Bang? The math simply doesn't add up if they grew the way black holes do today. The conventional wisdom goes like this: black holes form from collapsed stars, then slowly balloon by swallowing gas and merging with others. But in the dark ages, there wasn't enough time for that. A stellar mass black hole, even feasting non-stop, would take far longer than the universe's age to reach supermassive status. So what's the shortcut? One audacious idea is the direct collapse black hole. Imagine a primordial gas cloud so massive and dense hundreds of thousands of suns worth that it skips the star phase entirely. Under its own gravity, it implodes straight into a black hole, a ready-made heavyweight from birth. These titans could have been the seeds of today's galactic monsters, gulping down surrounding matter at breakneck speeds. Computer simulations show these chaotic nurseries, where gas flows in like water down a drain, fueling explosive growth. Then there's the primordial black hole theory, wild specks of space-time that might have formed microseconds after the Big Bang. Unlike stellar black holes, these wouldn't need stars to die first. If some were born hefty enough, they could have served as instant anchors for galaxies, growing rapidly as matter clustered around them. But the plot thickens with early galaxy mergers. Young galaxies were packed tight, colliding and tangling their central black holes together. Each merger would have created a more massive black hole, a snowball effect on a cosmic scale. Some might have even been kicked out, rogue black holes catapulted by gravitational waves, wandering the void. The James Webb Space Telescope is now spotting quasars from this era, their brilliance betraying black holes that shouldn't exist yet. Each discovery forces us to rethink the rules. Did exotic physics warp their growth? Could dark matter have played a role? One thing's certain: these runaway giants rewrite the story of how structures form, proving the early universe was far stranger than we ever imagined. Now, let's pivot to another cosmic head-scratcher, the case of the vanishing dwarf galaxies. If our simulations of the early universe are correct, there should be thousands of these tiny galaxies orbiting larger ones like the Milky Way. Yet when astronomers peer into the cosmos, they find only a fraction of that number. So where did the rest go? This discrepancy, known as the missing satellites problem, has been troubling scientists for decades, and the answers might rewrite our understanding of dark matter and galactic evolution. Imagine building a model of a city based on every known blueprint, only to step outside and find half the buildings are missing. That's essentially what's happening here. Supercomputer simulations, which factor in the gravitational pull of dark matter, predict a bustling cosmic neighborhood teeming with dwarf galaxies. But observations reveal a sparser reality. One leading theory points to dark matter's quirks. If dark matter particles behave differently than we assume, perhaps interacting with each other or with normal matter in unexpected ways, it could alter how dwarf galaxies form. Some might never coalesce, while others could dissolve before they fully take shape. Another possibility lies in the destructive tantrums of early stars. The first generations of stars were volatile behemoths, burning hot and dying young in colossal supernova. Their explosions would have blasted away surrounding gas, the raw material needed for dwarf galaxies to grow. Without enough fuel, these potential galaxies might have been stillborn, vanishing before they could shine. Even surviving dwarfs could have been stripped of their gas, leaving them faint and hard to spot, ghosts of the cosmos. Then there's the cannibalism angle. Larger galaxies like the Milky Way may have devoured their smaller neighbors over billions of years. Gravitational tugs could have torn dwarfs apart, scattering their stars into vast, barely detectable streams. Astronomers have already found such stellar rivers in our galaxy's halo, hints of past feasts. The James Webb Space Telescope is now hunting for these elusive dwarfs, probing deeper and fainter than ever before. Every new discovery, or lack thereof, forces us to question our models. Are we overestimating dark matter's role, underestimating the violence of the early universe? Or is there a darker, stranger explanation waiting to be uncovered? One thing's clear: the missing satellites problem isn't just about dwarf galaxies. It's a clue to the hidden rules governing everything we see and don't see in the cosmos. Turning to another cosmic puzzle that defies our expectations, let's unravel the mystery of the missing lithium. According to the Big Bang Theory, the universe should contain about 3 times more lithium than what we actually observe. This glaring discrepancy, known as the lithium abundance problem, has left scientists scratching their heads for decades. Picture this: in the first few minutes after the Big Bang, nuclear reactions forged the lightest elements, hydrogen, helium, and a tiny fraction of lithium. These predictions are incredibly precise, matching observed helium and hydrogen levels almost perfectly. But lithium, it's oddly scarce. Where did it go? One explanation points to stellar cannibalism. Over billions of years, stars like our Sun have been consuming lithium in their cores, effectively destroying it. As stars churn and mix their internal layers, lithium, a fragile element, gets broken down in the intense heat. This process could mean that much of the original lithium has been wiped out by generations of stars. But there's a twist: even younger stars, which haven't had time to burn through their lithium, still show lower than expected amounts. This suggests that something else is at play, perhaps an unknown quirk of particle physics. Some theories propose that hypothetical particles, like certain types of dark matter, could interact with lithium nuclei in ways that reduce their abundance. Others speculate that early cosmic phenomena like supernova or black hole activity might have altered lithium levels in ways we don't yet understand. Then there's the possibility that our measurements are flawed. Lithium is notoriously tricky to detect in space. It's often hidden in interstellar gas or locked away in hard-to-observe regions. Even slight errors in our detection methods could contribute to the mystery. The James Webb Space Telescope and next-generation observatories may finally provide answers. By analyzing the atmospheres of ancient stars or probing distant gas clouds, they could uncover clues about lithium's disappearance. Whether the solution lies in revised nuclear physics, overlooked cosmic processes, or something entirely unexpected, one thing is certain. Cracking the lithium problem could force us to rethink the very foundations of Big Bang cosmology. This isn't just about a missing element, it's about whether we've misunderstood one of the universe's earliest chapters. Every new discovery either reinforces our models or reveals gaps in our knowledge, and lithium's elusive nature keeps astronomers on their toes. The deeper we look, the more we realize just how much we have yet to learn about the cosmos. Now, let's pivot to a mystery that takes us to the very dawn of light itself, the elusive cosmic dawn. This is the moment when the first stars flickered to life, piercing the darkness of the early universe. Based on our best models, this cosmic sunrise should have happened around redshift 20, or roughly 180 million years after the Big Bang. But when the James Webb Space Telescope trained its sights on this ancient epoch, what it found left astronomers baffled. The problem: the galaxies Webb spotted are too bright, too massive, and too mature for their age. According to theory, the first stars should have been small, fragile things, giant, short-lived behemoths made almost entirely of hydrogen and helium. These so-called population 3 stars were expected to flicker out quickly, seeding the universe with heavier elements in violent supernova. But Webb's deep field images reveal galaxies that look like they've had time to grow and evolve far beyond what our timelines predict. One possible explanation is that star formation in the early universe was far more efficient than we thought. Maybe dense clouds of gas collapsed into stars at breakneck speed, creating galaxies that bulked up faster than our models allow. Or perhaps dark matter played a role. Its gravitational pull could have accelerated the clumping of matter, jump-starting galaxy formation earlier than expected. Then there's the wild card: what if the first stars weren't stars as we know them at all? Some theorists speculate about dark stars, hypothetical objects powered not by nuclear fusion but by the annihilation of dark matter particles. These bizarre entities could have grown to monstrous sizes, shining faintly in the infrared, exactly the kind of light Webb is designed to detect. If they existed, they might explain why some early galaxies appear brighter and more developed than they should. But the cosmic dawn mystery goes deeper. Even the timing of starlight's emergence is up for debate. Some observations of the cosmic microwave background suggest the first stars ignited earlier than redshift 20, while others hint at a later dawn. The universe's transition from darkness to light wasn't uniform. Some pockets may have lit up like cities at night, while others lingered in shadow for millions of years longer. This isn't just about tweaking a few equations. If our understanding of the cosmic dawn is wrong, it could mean rewriting the entire early history of galaxies. Webb's discoveries are forcing us to ask, did we underestimate the universe's creativity? Could there have been pathways to galaxy formation we haven't even imagined? Every new image from Webb is a clue, and with each one we're peeling back another layer of this ancient cosmic mystery. The search for answers is far from over. Upcoming observations, combined with advanced simulations, might finally reveal what truly happened during those first flickers of starlight. Until then, the cosmic dawn remains one of the most tantalizing puzzles of the Dark Ages, a reminder that the universe's earliest chapters still hold secrets we've only begun to uncover. But what if the cosmic dawn wasn't the only surprise waiting in the shadows of the early universe? Let's journey deeper into the cosmic Dark Ages, where an even stranger signal whispers secrets about the primordial gas that once filled the void. Astronomers call it the 21-centimeter anomaly, and it's one of the most baffling clues we've uncovered about the universe's infancy. Here's the puzzle. When scientists trained radio telescopes on hydrogen gas from just 200 million years after the Big Bang, they expected to see a predictable fingerprint, a specific absorption line caused by hydrogen atoms transitioning between energy states. But what they found was far colder and more pronounced than any model predicted. It's as if the early universe had a hidden cooling mechanism, a cosmic refrigerator that dropped temperatures lower than anyone thought possible. So what could have chilled the hydrogen so dramatically? One leading theory points to an unlikely culprit: dark matter. Normally, dark matter interacts with ordinary matter only through gravity, staying ghostly and aloof. But some physicists speculate that certain types of dark matter particles might have exchanged tiny amounts of energy with hydrogen atoms, subtly sapping their heat. Imagine billions of invisible particles acting like microscopic ice cubes, cooling the gas around them. This dark matter cooling could explain why the 21-centimeter signal dips so steeply. There's another twist. The signal isn't uniform. Some patches of the early universe seem much colder than others. That's led to wilder ideas like cosmic actions, hypothetical particles that could have clumped together, creating pockets of intense cooling. If true, it would mean dark matter wasn't just a passive scaffold for galaxies, but an active player in shaping the thermal landscape of the cosmos. Yet the plot thickens. Recent observations suggest the cooling might have happened too early, clashing with our current timeline of cosmic events. Could dark matter have properties we've completely overlooked, or is there another, even more exotic physics at work? Some theorists have proposed that early black holes or cosmic strings, fractures in space-time itself, might have contributed to the cooling, adding layers of complexity to the mystery. What makes this anomaly so thrilling is its sheer reach. The 21-centimeter signal isn't just a curiosity, it's a direct snapshot of the universe's toddler phase, a window into how dark and ordinary matter danced together long before stars existed. If we can decode it, we might finally understand how dark matter behaves on scales no lab experiment can replicate. For now, the hydrogen signal remains a tantalizing enigma, a cosmic whisper from an era when the universe was still figuring itself out. New radio telescopes like the upcoming Square-Kilometer Array aim to map this signal in unprecedented detail, potentially revealing whether dark matter really did leave its chilly fingerprints on the dawn of time. Until then, the mystery of the anomalously cold hydrogen stands as a quiet challenge to our understanding of the cosmos's darkest age. But just as we grapple with the chilling whispers of ancient hydrogen, another cosmic question emerges from the shadows. What if the very fabric of space-time wasn't as steady as we assumed during those dark, starless eons? Let's turn our attention to one of the most elusive forces in the universe: dark energy. This is the puzzle. For decades, astronomers have treated dark energy as a constant force, a kind of cosmic glue that's been steadily pushing the universe apart since the Big Bang. But what if that's not the whole story? Some theorists now suspect dark energy's strength might have flickered during the cosmic dark ages, like a dimmer switch being subtly adjusted. Imagine the universe's expansion speeding up or slowing down in fits and starts, long before galaxies even had a chance to form. That's the tantalizing possibility behind phantom dark energy fluctuations. Here's why it matters. If dark energy did vary during this era, it would leave a distinct fingerprint on the way the universe expanded. Think of it like a balloon inflating in uneven bursts. Some regions would stretch faster than others, subtly warping the distribution of matter. We might even see hints of this in the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature variations in that ancient light could betray moments when dark energy's push grew stronger or weaker. But how could we test such a radical idea? Enter the future LISA mission, a space-based gravitational wave observatory set to launch in the next decade. Unlike ground-based detectors, LISA will listen for the faintest ripples in spacetime from collisions of supermassive black holes, events dating back to near the cosmic dawn. If dark energy's strength fluctuated, those gravitational waves would carry subtle distortions like echoes of a changing cosmic tempo. It's a long shot, but if LISA picks up these whispers, it could rewrite our understanding of dark energy altogether. Of course, not everyone's convinced. Skeptics argue that the data we have so far fits just fine with constant dark energy, and that inventing fluctuations adds unnecessary complexity. But others counter that the cosmic dark ages are still a vast, uncharted territory. Who's to say dark energy didn't behave differently before stars lit up the universe? After all, this was an era when even fundamental forces might have played by different rules. One thing's certain: if dark energy did fluctuate, it would upend our models of cosmic evolution. Maybe the universe's expansion wasn't as smooth as we thought. Maybe dark energy isn't a static force but something far more dynamic, evolving alongside the cosmos itself. For now, we're left with a haunting possibility that the darkest age of the universe might hold secrets not just about its past, but about its ultimate fate. And with missions like LISA on the horizon, we may soon find out whether those phantom fluctuations are real or just another cosmic mirage. Now, as we wrestle with the enigma of dark energy's phantom fluctuations, another startling cosmic discovery demands our attention, one that challenges the very timeline of the universe's evolution. The James Webb Space Telescope has stumbled upon something utterly baffling: galaxies that seem to have grown up far too fast. These aren't the fragile, newborn galaxies we expected to find in the universe's toddler years. No, these are cosmic behemoths, massive, mature, and fully formed, appearing shockingly early in cosmic history. Picture this: you're flipping through a family photo album, expecting to see baby pictures of the universe. Instead, you find snapshots of what looks like a cosmic adult, muscles and all, posing in the crib. That's the scale of the problem. According to our best models, galaxies this big and well-structured shouldn't exist until much later. Yet there they are, glowing in JWST infrared eye, defying expectations like uninvited guests at a cosmic party. So what's going on? One possibility is that our cosmology timeline is simply wrong. Maybe the universe got a head start we didn't account for, compressing billions of years of galactic growth into a fraction of the time. But that's a radical rewrite, one that would send textbooks back to the printing press. The alternative: that some exotic, unknown physics turbocharged galaxy formation. Imagine a hidden cosmic cheat code, perhaps involving dark matter interactions or even wilder ideas like primordial black holes seeding early growth. Here's where it gets even stranger. These overweight infant galaxies aren't just big, they're also suspiciously bright, packed with stars that shouldn't have had time to form. One leading theory suggests that early stars might have been born under unusual conditions, like hyper-efficient star factories operating in overdrive. Or perhaps mergers between young galaxies happened at breakneck speed, fueled by denser pockets of dark matter. But not everyone's ready to toss out the standard model. Some researchers argue that JWST might be seeing these galaxies through gravitational lenses, natural cosmic magnifying glasses that distort and amplify distant objects, making them appear larger and brighter than they really are. Others propose that dust in the early universe could be playing tricks on us, reddening the light of these galaxies and making them seem more mature than they are. Yet with each new JWST observation, the evidence for these precocious galaxies grows stronger. If they're real, the implications are staggering. It would mean that the universe's childhood was far more dynamic and chaotic than we ever imagined, a place where galaxies grew up fast, breaking all the rules. And that raises an even deeper question. What other surprises are lurking in the cosmic dark ages, waiting to upend our understanding of how the universe works? For now, the mystery of the overweight infant galaxies remains wide open. Are they cosmic anomalies or signs of a deeper truth hidden in the shadows of the early universe? As JWST peers further back in time, we may finally get our answer, and with it, either a tweak to our cosmic calendar or a revolution in physics itself. Now, as we grapple with the puzzle of those unexpectedly mature galaxies, our cosmic detective work leads us to another head-scratching mystery, one involving matter that seems to have vanished without a trace. We're talking about the case of the missing baryons, the ordinary building blocks of stars, planets, and even you and me. Here's the conundrum. When we tally up all the ordinary matter that should exist based on the Big Bang's chemical cookbook, about half of it is simply gone. Not hiding in stars, not floating as gas, just missing. It's like carefully counting every ingredient for a cake, mixing them together, and then finding half your batter has disappeared before it even hits the oven. Scientists call this the missing baryon problem, and it's been haunting cosmology for decades. But where could all this matter be hiding? The prime suspect is something called the warm-hot intergalactic medium, or WIM for short. Picture this as the universe's version of a steamy sauna, a diffused network of superheated gas filaments weaving between galaxies, so thin and spread out that it's nearly invisible to our telescopes. This gas isn't cold enough to form stars, nor dense enough to glow brightly, making it fiendishly hard to detect. The hunt for WIM has turned into a cosmic game of hide and seek. Astronomers use clever tricks like watching how it absorbs light from distant quasars, those brilliant beacons from the early universe. When quasar light passes through WIM tendrils, certain wavelengths get absorbed, leaving faint fingerprints in the light spectrum. It's like spotting someone's breath on a cold day. You can't see the person, but the mist gives them away. Recent X-ray telescopes have started catching glimpses of this elusive material. Observations suggest WIM might be hiding a significant chunk of those missing baryons, perhaps even most of them. But there's a twist. The gas is so hot, millions of degrees, and so spread out that even these detections only account for part of the missing matter. Some could be lurking in even harder to spot forms, like ultra-diffuse clouds or strange states of matter we haven't yet imagined. What makes this mystery so crucial is that baryonic matter, unlike dark matter, is the stuff we're made of. If we can't account for half of it, our understanding of how galaxies form and evolve has a gaping hole. Finding these missing baryons would complete the cosmic inventory, letting us finally balance the universe's books. As next-generation telescopes sharpen their focus, we may soon solve this decades-long puzzle. Until then, the missing baryons remain one of cosmology's most persistent ghosts, a reminder that even the ordinary can be extraordinary when it decides to hide in plain sight. Now, shifting our gaze to an even more enigmatic possibility lurking in the cosmic shadows, we encounter a theory so bizarre it sounds like science fiction: dark stars. These aren't your typical twinkling celestial bodies. Imagine, if you will, a star that doesn't shine by nuclear fusion like our sun, but instead glows from the annihilation of dark matter. That's the mind-bending premise behind dark stars, hypothetical giants that could rewrite our understanding of the universe's first luminous objects. Here's how it might work. In the early universe, dense clumps of dark matter could have gathered in the cores of collapsing gas clouds. As dark matter particles collided and annihilated, they'd release intense heat, preventing the gas from fragmenting into smaller stars. Instead, you'd get a single, monstrously large object, a dark star, potentially stretching hundreds of times wider than our solar system and glowing with an eerie infrared light. These behemoths wouldn't just be big, they'd be unstable, teetering on the edge of collapsing into black holes once their dark matter fuel ran out. But how do we hunt for something that might not even exist? Enter the James Webb Space Telescope, our best hope for spotting these cosmic oddities. Dark stars, if they're out there, would emit a unique infrared signature, a soft, diffuse glow unlike the sharp light of regular stars or quasars. JWST powerful infrared eyes are perfectly tuned to pick up these subtle whispers from the early universe. some researchers are already scouring its deep field images for unusually large, faint objects that could fit the dark star profile. What makes this search so thrilling is the stakes. If dark stars are real, they'd solve multiple cosmic puzzles at once. They could explain why some early galaxies in JWST data appear unexpectedly massive. Dark stars may have seeded them with colossal black holes. They might even account for part of the universe's missing baryons, as their formation would lock away ordinary matter in bizarre, long-vanished structures. Of course, skepticism remains. Dark matter's true nature is still unknown, and without direct proof of its ability to annihilate, dark stars stay in the realm of captivating speculation. Yet that's the beauty of cosmic mysteries. They push us to imagine the unimaginable. Whether JWST uncovers these ghostly giants or not, the hunt for dark stars reminds us that the universe's early chapters might be stranger than anything we've dared to dream. And with every new observation, we're one step closer to separating cosmic myth from reality. Now, let's turn our attention to another cosmic enigma, one that's invisible yet profoundly shapes the universe: the origins of cosmic magnetic fields. These fields weave through galaxies, guiding the motion of gas and dust, but their beginnings remain one of the most perplexing puzzles of the Dark Ages. How did magnetic fields emerge in a universe that, early on, lacked the stars and galaxies needed to generate them through conventional means? Here's the head-scratcher. Normally, magnetic fields arise from dynamos rotating, electrically conductive fluids like molten metal in a planet's core or ionized gas in stars. But in the infant universe, before the first stars flickered to life, there were no dynamos to speak of. So where did these fields come from? One leading idea points to the primordial soup of particles that filled the cosmos just moments after the Big Bang. In those chaotic first seconds, quantum fluctuations or phase transitions in the searing hot plasma might have imprinted weak magnetic seeds across the fabric of space-time. These faint traces, amplified over eons by the motion of ionized gas, could have grown into the vast intergalactic fields we detect today. To test this, scientists rely on sophisticated plasma physics simulations. These virtual experiments recreate the conditions of the early universe, tracking how tiny magnetic ripples could stretch and strengthen as the cosmos expanded. Some models suggest that turbulence in the primordial plasma, driven by shocks from the first supernova or the violent growth of black holes, acted like a cosmic amplifier, boosting weak fields into the structured patterns we now observe. Others propose even wilder mechanisms, like phase transitions in the fundamental forces of nature, which could have generated magnetic fields as a byproduct. The stakes are high. If primordial fields exist, they'd offer a window into physics beyond the standard model, perhaps even clues about dark matter or extra dimensions. They could also explain anomalies in the cosmic microwave background or the puzzling alignment of distant quasars' light, but detecting these ancient fields isn't easy. Today's telescopes hunt for their fingerprints in the polarized light of distant galaxies or the subtle distortion of radio waves traveling through intergalactic space. What makes this mystery so tantalizing is its universality. Magnetic fields thread through every galaxy, every cluster, even the voids between them, yet their origins might lie in processes so exotic they defy our current understanding. Whether born from quantum froth or hidden dimensions, solving this riddle wouldn't just illuminate the Dark Ages. It would reveal a fundamental thread woven into the very fabric of reality itself. Now, shifting our gaze to another cosmic puzzle, we encounter a startling mismatch between theory and observation, the case of the missing supernova. According to our best models, the early universe should have been lit up like a fireworks display by countless exploding stars. These cataclysmic events, marking the deaths of the first massive stars, ought to have left behind a wealth of chemical signatures and visible remnants. Yet when we look back to the cosmic Dark Ages, the evidence is strangely scarce. Where did all those supernovae go? one compelling explanation revolves around the nature of the first stars themselves. Known as Population 3 stars, these pioneers were made almost entirely of hydrogen and helium, lacking the heavier elements that define later generations. Their sheer size, often hundreds of times more massive than our Sun, meant they lived fast and died violently. But here's the twist: the most massive of these stars might not have left behind the usual supernova remnants we're familiar with. Instead, they could have undergone even more extreme explosions like hypernova or pair instability supernova, which obliterate the star so completely that little to no trace remains. Hypernova are thought to be up to 100 times more energetic than typical supernova, linked to the birth of black holes and gamma-ray bursts. Pair instability supernova, on the other hand, occur when a star's core becomes so hot that light itself starts converting into electron-positron pairs. This saps the core's pressure, causing a runaway collapse that ends in a total explosion. No neutron star or black hole left behind, just a spray of heavy elements hurled into the cosmos. If these events dominated the early universe, their lack of visible remnants would suddenly make sense. Another possibility is that the first supernova were simply too early for us to spot. The light from these explosions has been traveling for over 13 billion years, stretched and dimmed by the expansion of the universe. By the time it reaches us, the faint afterglow might be indistinguishable from the background noise of cosmic radiation. Or perhaps the chemical debris from these explosions was quickly swept up into new generations of stars, leaving no isolated clouds for us to detect. The implications are profound. If pair instability supernova were common, they could explain why certain heavy elements like gold and platinum appear in younger stars at higher quantities than expected. These titanic blasts would have been cosmic forges, seeding the universe with materials essential for planets and life. Yet their very efficiency at dispersing these elements might also explain why we can't find their ruins today. Solving this mystery isn't just about filling a gap in our cosmic timeline. It's about understanding how the earliest stars shaped the universe we see around us. Future telescopes like the James Webb Space Telescope's successors may finally catch the faint echoes of these ghostly explosions. Until then, the phantom supernova surge remains one of the Dark Age's most elusive riddles. But here's something even wilder to consider. What if time itself wasn't behaving the way we think during the cosmic Dark Ages? This brings us to our next enigma: the puzzling time stream anomalies that might be warping our cosmic observations. Imagine staring into the deep past, only to realize the universe's own expansion could be playing tricks on our perception of time. Einstein's theory of relativity tells us that massive objects warp spacetime, slowing time in their vicinity. Near black holes, this effect becomes extreme, a phenomenon called gravitational time dilation. But what if the universe's explosive early growth stretched spacetime so dramatically that time didn't flow uniformly everywhere? In those first chaotic moments, regions with denser concentrations of matter might have experienced time at a radically different pace than emptier voids. The light and signals we observe today from the Dark Ages could carry distortions, like a cosmic funhouse mirror reflecting events out of sequence. Think of it this way: if two stars formed at the same cosmic instant but in different environments, one in a dense proto-galaxy, the other in a sparse region, their clocks wouldn't tick in sync. The star in the crowded area might age slower from our distant vantage point, making it appear younger than its isolated counterpart. This could explain why some early galaxies observed by the James Webb Space Telescope seem improbably mature for their era. Their development might not defy physics. We might just be seeing their history stretched or compressed by the universe's warped timeline. Black holes offer a striking analogy. To an outside observer, a spaceship falling toward a black hole would appear to slow down, eventually freezing at the event horizon as time grinds to a halt. But for the crew on board, time would feel normal, Similarly, if a supermassive black hole existed in the early universe, its extreme gravity could have created time-delayed echoes of nearby events. A supernova's light might reach us billions of years after the actual explosion, creating ghostly apparitions in our telescopes. There's even speculation that these time distortions could hide entire epochs of cosmic history. If a phase of rapid inflation stretched space-time unevenly, some signals from the Dark Ages might still be in transit, while others arrived eons ago. It's like receiving pages from a book out of order without the correct sequence. The story becomes impossible to piece together. The implications are staggering. If time dilation skews our observations, we might be misjudging the timing of key events, from the birth of the first stars to the formation of galaxies. Future telescopes could resolve this by pinpointing inconsistencies in redshift data or identifying time-lagged objects that defy conventional aging models. Until then, this temporal puzzle reminds us that the universe's greatest trick might be hiding its past in plain sight. And speaking of hidden layers, our next mystery dives into an even stranger possibility that the fabric of spacetime itself might bear the scars of quantum chaos. Now, let's peel back another layer of the cosmic onion to examine something even more fundamental, the very fabric of reality. If spacetime itself could whisper secrets from the dawn of the universe, what would it tell us? This brings us to the haunting echoes of quantum foam, a turbulent sea of fluctuations that might have left fingerprints on the oldest light in the cosmos. At the smallest scales, spacetime isn't smooth and continuous like a sheet of glass. Instead, it's a frothing, bubbling mess of quantum fluctuations, often called quantum foam. Picture an ocean in a storm, with waves and bubbles constantly forming and vanishing. These tiny, ephemeral distortions in spacetime are thought to have been even more violent during the universe's infancy, when energies were unimaginably high. The question is, did this quantum chaos leave any trace on the cosmic microwave background, the afterglow of the Big Bang? Loop quantum gravity, one of the leading theories attempting to unify quantum mechanics and general relativity, suggests these fluctuations could have imprinted subtle patterns on the early universe's radiation. Think of it like throwing a handful of pebbles into a pond. The ripples they create might interfere with each other, leaving behind a unique signature. Similarly, quantum foam's chaotic jittering might have altered the polarization or temperature variations in the cosmic microwave background in ways we're only beginning to detect. The Planck satellite, a cosmic time machine launched by the European Space Agency, has been scouring the sky for these faint echoes. Its ultra-precise measurements of the microwave background have revealed tiny anomalies, hints of asymmetry or unexpected swirls in the radiation's polarization. Some scientists speculate these could be the faint scars of quantum foam's reign, a cosmic graffiti left over from when the universe was less than a trillionth of a second old. But proving this isn't easy. Quantum effects are notoriously slippery, and the signals we're hunting are buried under eons of cosmic noise. It's like trying to hear a whisper in a hurricane. Yet, if we can isolate these echoes, they'd revolutionize our understanding of gravity itself. For instance, they might reveal whether spacetime is fundamentally made of discrete loops, a core prediction of loop quantum gravity, or if it behaves entirely differently at the smallest scales. What makes this mystery so tantalizing is its potential to bridge the greatest divide in physics, the gap between quantum mechanics and Einstein's relativity. The cosmic dark ages might seem like a quiet era, but beneath the surface, the universe's quantum heartbeat could still be pulsing, waiting for us to decode its rhythm. And as we turn the page to our next enigma, we'll explore an idea that pushes the boundaries of reality even further, hidden dimensions lurking just beyond our perception. Now, let's stretch our imaginations beyond the familiar 3 dimensions of space and 1 of time. What if the cosmos holds secrets in dimensions we can't even see? This is where string theory's hidden dimensions come into play, a wild idea that might explain some of the strangest puzzles from the cosmic dark ages. String theory, one of the most ambitious frameworks in physics, suggests that the universe isn't just the 4 dimensions we experience. Instead, it could have as many as 10 or 11 dimensions, all curled up so tightly that they're invisible to us, like ants crawling on a wire that's too thin for us to notice. These compactified dimensions might sound like science fiction, but they could play a crucial role in shaping the universe during its earliest, most mysterious phases. Here's where it gets fascinating. During the Dark Ages, these extra dimensions might have influenced how gravity behaved, how particles interacted, or even how the first structures in the cosmos formed. Picture a garden hose lying on the ground. From a distance, it looks like a simple line, one dimension, but up close, you see it's actually a tube with a circular dimension wrapped around it. Similarly, hidden dimensions could have left subtle fingerprints on the universe's evolution, like altering the strength of gravity or allowing exotic particles to exist briefly before vanishing. One compelling idea from string theory is brain cosmology. Imagine our universe as a 3-dimensional brain floating in a higher dimensional space, like a slice of bread in a multi-dimensional loaf. Other brains could exist parallel to ours, and collisions between them might have sparked events like the Big Bang or triggered bursts of energy during the Dark Ages. Some theories even suggest that dark matter could be particles trapped on a nearby brain, just out of reach but still tugging on our universe through gravity. But how do we test something so abstract? Scientists look for clues in the cosmic microwave background or in the behavior of gravity at tiny scales. If extra dimensions exist, they might cause gravity to behave slightly differently than Einstein predicted, perhaps weakening faster over short distances. Experiments with ultra-precise gravity measurements or particle colliders could one day reveal these hidden layers of reality. The beauty of this mystery is its sheer audacity. It forces us to rethink what reality even means, and as we peel back these theoretical layers, we edge closer to answering whether the cosmic dark ages were shaped by forces beyond our current comprehension. Next, we'll turn our attention to another ghostly relic of the early universe: neutrinos, the universe's most elusive messengers. But before we chase after parallel universes, let's focus on something equally elusive yet right under our noses, or rather streaming through them. Every second, trillions of nearly invisible particles called neutrinos pass through your body without a trace. These cosmic ghosts, born in the aftermath of the Big Bang, could hold the key to understanding the Dark Ages in a way no other particle can. Think of neutrinos as the universe's silent witnesses. Unlike the cosmic microwave background, which paints a vivid picture of the universe 380,000 years after the Big Bang, the cosmic neutrino background is far older, emerging just 1 second after creation. These relic neutrinos are like whispers from the universe's first breath, carrying pristine information about conditions before even the first stars flickered to life. But here's the catch: they barely interact with matter. A neutrino could sail through a light year of lead without a single collision. So how do we hunt particles that refuse to be caught? Enter IceCube, the most ambitious neutrino detector on Earth. Buried deep in the Antarctic ice, this colossal array uses over 5,000 optical sensors to spot the rare flashes of light produced when a neutrino, against all odds, strikes an atom. It's like listening for a pin drop in a hurricane, but when IceCube does detect a neutrino, it's a triumph. These detections help us map high-energy cosmic events, and someday, they might even snag one of those primordial neutrinos from the Big Bang itself. Why does this matter? Because neutrinos could unlock mysteries that light alone can't. During the Dark Ages, their sheer numbers and weak interactions meant they shaped how matter clumped together, subtly influencing where galaxies would later form. Some theories even suggest neutrinos might have slowed down structure formation, explaining why the universe looks smoother than our models predict. And if we ever detect the cosmic neutrino background, It would be like uncovering a fossilized echo of the universe's infancy, filling in gaps that the cosmic microwave background leaves blank. The quest for these ghostly particles is more than a technical challenge, it's a philosophical one. In a cosmos dominated by forces we can see, neutrinos remind us that the most transformative clues often lie in what we can't. As detectors grow more sensitive and theories more refined, we edge closer to hearing the universe's oldest, faintest story. Up next, we'll confront an even bolder idea. What if the Dark Ages weren't the same in every universe? The multiverse beckons. Now let's stretch our imaginations beyond the confines of our own universe. What if the cosmic Dark Ages played out differently elsewhere, not just in distant galaxies, but in entirely separate realities? This brings us to the mind-bending idea of parallel universes, where the rules we take for granted might not apply at all. Picture the multiverse like a vast ocean of soap bubbles, each bubble a self-contained universe with its own unique physics, history, and maybe even its own version of the Dark Ages. In some of those bubbles, the first stars might have ignited earlier, bathing the cosmos in light while our universe was still shrouded in darkness. In others, dark matter could have behaved differently, leading to galaxies shaped like spirals instead of clumps, or no galaxies at all. The possibilities are as endless as the bubbles themselves. One compelling framework for this comes from quantum mechanics, where every decision or random event spawns branching timelines. Imagine the universe's first moments as a tree with countless limbs, each branch representing a different outcome. In one branch, primordial density fluctuations might have been stronger, causing stars to form in a frenzy. In another, weaker fluctuations could have left the cosmos languishing in darkness longer. These branches aren't just theoretical, they're mathematically grounded in the many worlds interpretation of quantum physics. But how do we test something as intangible as other universes? Astronomers look for fingerprints in our own cosmos. For instance, if another universe collided with ours during the Dark Ages, it might have left a bizarre pattern in the cosmic microwave background, like a bruise on the sky. Others search for anomalies in fundamental constants. What if the strength of gravity or the mass of an electron varies in other bubbles? Such discoveries could hint that our universe isn't the only one playing by its own rules. The multiverse idea also reshapes how we view our cosmic origins. If endless variations exist, then the Dark Ages weren't a singular event, they were a spectrum of possibilities. Some universes might have skipped the Dark Ages entirely, while others might still be trapped in them. It's humbling to think that our reality, with its specific timeline of starlight and structure, is just one version of the story. As we push the boundaries of cosmology, the multiverse forces us to ask bigger questions. Are we in the universe where things turned out typical, or is our version the outlier? The answers might lie in the subtle clues hidden in our skies, or in the faint echoes of universes we'll never see. Up next, we'll tackle another radical puzzle. Did gravity itself behave differently during the Dark Ages, warping the very fabric of cosmic history? Now let's shift our focus to one of the most fundamental forces in the cosmos, gravity. But here's the twist: what if gravity didn't always behave the way it does today? Some scientists speculate that during the cosmic Dark Ages, gravity might have moved faster than light, reshaping how structures like galaxies and stars formed in the universe's infancy. To understand why this idea is so radical, let's rewind to what we know. In our everyday experience, gravity follows Newton's laws. Objects attract each other based on their mass and distance. Then came Einstein, who redefined gravity not as a force but as the curvature of spacetime itself. According to his theory of general relativity, gravity travels at the speed of light. But what if that wasn't always the case? Imagine the early universe, a seething hot soup of particles and energy. If gravity moved faster back then, its influence would have reached farther and faster, pulling matter together more efficiently. This could explain why we see massive galaxies and supermassive black holes so early in cosmic history, structures that, under our current understanding, shouldn't have had enough time to form. Some modified gravity theories, like modified Newtonian dynamics, suggest that gravity's strength or behavior might change under extreme conditions, such as the ultra-dense environment of the young cosmos. But how do we test such a bold idea? One clue lies in the cosmic microwave background, the afterglow of the Big Bang. If gravity propagated faster, it would have left subtle imprints in this ancient light patterns that deviate from what standard models predict. Another approach involves studying gravitational waves, ripples in spacetime from cataclysmic events like black hole mergers. If these waves arrived slightly earlier than their accompanying light signals, it could hint that gravity once outpaced light itself. Of course, not everyone agrees. Critics argue that tampering with gravity's speed creates more problems than it solves, potentially throwing off other well-tested predictions of cosmology. Yet the mystery persists, pushing scientists to refine their models and dig deeper into the data. Whether gravity played by different rules in the past or not, the question itself challenges our understanding of the universe's most familiar force. Next, we'll venture into an even stranger possibility, that the Dark Ages were shaped not by familiar matter, but by swarms of tiny primordial black holes lurking unseen in the cosmic shadows. Now let's peel back another layer of cosmic mystery, one that takes us deep into the shadows of the early universe. Picture this: countless tiny black holes, no bigger than asteroids, born in the chaotic aftermath of the Big Bang. These aren't the colossal black holes we know today, but primordial ones, lurking unseen and potentially solving one of cosmology's biggest puzzles: the nature of dark matter. What makes primordial black holes so intriguing? Unlike the black holes formed from collapsing stars, these could have sprung into existence when the universe was just a fraction of a second old. Density fluctuations in the searing hot plasma of the early cosmos might have created regions so dense they collapsed directly into black holes. Some theories suggest they could range in size from a grain of sand to a small moon, packing the mass of a mountain into a space smaller than an atom. If these tiny titans exist in vast numbers, they could explain why we can't find most of the universe's matter. Dark matter doesn't interact with light, yet its gravitational pull shapes galaxies and bends spacetime. Primordial black holes fit the bill. They're invisible, massive, and would behave just like dark matter. But how do we detect something so elusive? One clue lies in their subtle fingerprints on the cosmos. When light from distant stars passes near a black hole, its path bends, creating a phenomenon called gravitational lensing. A swarm of primordial black holes would warp starlight in a unique way, leaving telltale flickers or distortions in the night sky. Telescopes like Hubble and the upcoming Nancy Grace Roman Space Telescope are scanning for these tiny flashes, hunting for shadows of the unseen. There's another twist: Hawking radiation. Stephen Hawking predicted that black holes slowly evaporate, emitting particles over time. The smaller the black hole, the faster it vanishes. Asteroid-sized primordial black holes would be radiating away their energy right now, possibly leaving behind bursts of gamma rays or other high-energy signals. Detecting these faint whispers could confirm their existence or rule them out entirely. Yet the idea isn't without controversy. Some argue that primordial black holes would have disrupted the early universe too much, altering the cosmic microwave background in ways we don't observe. Others counter that if they're clustered just right, they could avoid these pitfalls. It's a cosmic balancing act, and the answer might lie in the next generation of telescopes and detectors. Whether these ancient remnants are the missing dark matter or not, their existence would rewrite the story of the universe's infancy. Up next, we'll explore how early black holes might hold the key to another enigma: the baffling disappearance of information in the cosmos. Now let's untangle one of the most mind-bending puzzles in modern physics, a cosmic magic trick where information seems to vanish without a trace. Black holes don't just swallow stars and gas, they might be erasing the very fabric of reality's code. Here's the problem: according to quantum mechanics, information can never truly be destroyed. Every particle, every interaction leaves a fingerprint in the universe. But when something falls into a black hole, that information appears to be lost forever. Stephen Hawking's groundbreaking work revealed that black holes aren't completely black, they emit radiation and slowly evaporate over eons. Yet this Hawking radiation seems random, like static noise, with no trace of the original material that formed the black hole. That's the information paradox, and it threatens to unravel our understanding of physics at the deepest level. So where does the information go? One radical idea comes from the holographic principle, which suggests that all the data swallowed by a black hole isn't lost, it's smeared across its event horizon like a cosmic hard drive. Imagine a two-dimensional surface encoding everything that falls into the three-dimensional abyss below. It's as if the universe is projecting a hologram, preserving information in a way we don't yet fully understand. Some theorists argue that when a black hole evaporates, this encoded data is somehow returned to the cosmos, scrambled but intact. Others propose even wilder solutions, like hidden parallel universes or secret tunnels in spacetime called quantum wormholes. Early black holes from the cosmic dark ages could hold the key to solving this mystery. If primordial black holes, those tiny relics we discussed earlier, evaporated quickly due to their small size, their death throes might have left behind subtle imprints in the ancient universe. Future telescopes could hunt for these signatures, potentially revealing whether information truly escapes or is forever locked away. The stakes couldn't be higher. If information is lost, we'd need to rewrite quantum theory. If it's preserved, we might uncover a hidden layer of reality where spacetime itself is a projection of deeper, more fundamental laws. This isn't just academic curiosity, it's a battle for the soul of physics. Einstein's general relativity says black holes destroy information. Quantum mechanics says they can't. Whoever wins, our understanding of the universe will never be the same. And with that, we turn to another cosmic curveball. Could time itself be playing tricks on us during the Dark Ages? Now, let's venture into one of the most controversial ideas in cosmology, a theory that turns our cosmic clock upside down. What if the Dark Ages weren't as short as we think? What if time itself played a trick on us, stretching this shadowy epoch far longer than our telescopes suggest? This is the phantom time hypothesis, a bold challenge to the universe's official timeline. At the heart of this mystery lies a simple but unsettling question: could we be misreading the universe's history? Our understanding of the cosmic dark ages relies heavily on redshift, the stretching of light from distant galaxies as the universe expands. The farther away an object is, the more its light shifts toward the red end of the spectrum, telling us how long that light has traveled. But what if redshift isn't just about expansion? Enter the tired light theory, an alternative idea suggesting that light loses energy over vast distances due to interactions with space itself, not because the universe is stretching. If true, this would mean some of the oldest galaxies we observe might not be as ancient as we believe. The Dark Ages could have lingered much longer, with the first stars flickering to life later than our models predict. Critics argue that tired light contradicts overwhelming evidence for cosmic expansion, like the cosmic microwave background and the precise distribution of galaxies. Yet, proponents point to odd anomalies, galaxies in the early universe that appear too mature, or hydrogen signals that don't quite match predictions. Could these discrepancies be clues that our timeline is off? Some researchers even speculate that gravitational waves or quantum effects in the early universe might have warped time's flow, making certain periods appear shorter or longer than they truly were. The stakes here are enormous. If the Dark Ages stretched longer than recorded, it would rewrite the story of how galaxies formed, how black holes grew, and even how life's building blocks emerged. It would force us to rethink the very pace of cosmic evolution. Future telescopes like the Nancy Grace Roman Space Telescope could settle the debate by hunting for subtle time signatures in ancient light. Until then, the phantom time hypothesis remains a tantalizing what-if, one that reminds us how much we still don't know about the universe's deepest past. And speaking of cosmic illusions, our final mystery takes us to the ultimate question. What did the Dark Ages whisper about the universe's fate? Now, as we pull back the cosmic curtain one last time, we arrive at a question that has haunted humanity since we first looked up at the stars. How does this all end? The Dark Ages didn't just shape the universe's past, they may hold cryptic clues about its ultimate fate. Hidden in the faint whispers of those early epochs could be the answer to whether our cosmos will fade into icy stillness, tear itself apart, or vanish in a blink. Let's start with the most chilling scenario, the Big Freeze, also known as heat death. Imagine a universe where entropy, the slow unraveling of order into chaos, finally wins. Stars burn out, black holes evaporate, and space stretches so thin that even atoms pull apart. The Dark Ages offer a preview of this, a time when the universe was cold, dark, and nearly lifeless. But here's the twist: the way matter clumped together back then, the faint imbalances in the cosmic microwave background, might tell us if this icy fate is inevitable. Some models suggest that if dark energy keeps accelerating expansion, galaxies will vanish over the horizon, leaving us alone in an empty void. Then there's the more dramatic option, the Big Rip. If dark energy grows stronger over time, it could overcome gravity, shredding galaxies, then stars, and finally atoms themselves. The eerie silence of the Dark Ages, those vast stretches of nothingness, might hint at this fragility. Researchers scour ancient hydrogen signals for signs of dark energy's early behavior. Did it fluctuate? Was it stronger back then? A single anomaly could signal that the cosmos is on a countdown to self-destruction. But the wildest possibility comes from quantum physics, vacuum decay. Picture the universe as a bubble perched on a precarious ledge. If a quantum trigger destabilizes the fabric of spacetime, a new alien physics could surge outward at light speed, rewriting reality in an instant. The Dark Ages' extreme conditions, those moments of searing heat and crushing density, might have left behind relics like primordial black holes or strange particles that act as ticking time bombs. If one decays, it could spawn a new Big Bang or oblivion. The irony is profound. The era we call the Dark Ages might illuminate our future. Telescopes like JWST and the upcoming Nancy Grace Roman Space Telescope are now piecing together these clues, mapping how structures formed in the early universe to predict how they'll crumble. Every galaxy they spot, every wisp of ancient gas, is a breadcrumb on the trail to eternity. So as we close this journey through the cosmos' greatest mysteries, remember, the universe's first chapters and its last are written in the same ink. The Dark Ages aren't just a blank page in history, they're a mirror, reflecting both our origins and our destiny. And with that, we've reached the end of our exploration. But the real adventure lies ahead as science chases these cosmic shadows into the light. If these mysteries captivated you, don't forget to like, subscribe, and join us in the comments. What's your bet on how the universe ends? As we reflect on this cosmic journey through the darkest chapters of our universe's history, one truth becomes clear. These 25 mysteries aren't isolated riddles, they're threads in a grand, interconnected tapestry. From the missing first stars to the whispers of dark matter, from runaway black holes to phantom dimensions, each puzzle holds a piece of the bigger picture. It's as if the universe left us a detective story written in the language of gravity, light, and time, and we're only just beginning to decipher its clues. What makes these mysteries so thrilling is how they weave together. The great cosmic silence might be tied to the scarcity of early life, while the lithium problem could hint at undiscovered physics that also shaped dark energy. Even the vanishing dwarf galaxies and the overweight infant galaxies might be two sides of the same cosmic coin, revealing flaws in our understanding of structure formation. Every answer we chase leads to new questions, pulling us deeper into the mystery. But here's the exciting part: we're not solving this puzzle alone. The James Webb Space Telescope is already rewriting textbooks with its stunning deep-field images, while upcoming missions like the Nancy Grace Roman Telescope and LISA will probe dark energy's secrets and listen for gravitational waves from the universe's infancy. Groundbreaking experiments hunting for actions or cosmic neutrinos could crack the dark matter enigma within our lifetimes. So, as we close this cosmic case file, remember, you're witnessing science in real time. Every observation, every dataset brings us closer to turning these mysteries into breakthroughs. And that's where you come in. Stay curious, follow the journey of these telescopes, and who knows, maybe one day you'll be the one connecting the dots in the comments or even in a research lab. If this voyage through the dark ages left you awestruck, don't forget to hit like and subscribe. It fuels our mission to explore the universe's greatest enigmas. Drop your favorite mystery in the comments below. Are you team primordial black holes or team dark stars, skeptical about phantom dimensions or all in on the multiverse? Let's keep the conversation starlit. Until next time, keep looking up. The cosmos still has plenty of secrets to share.